Okay, so today we will be looking at range and null space of a linear transformation, and then the dimensions, how to find their bases, and also we will be looking at composition of linear transformations and so on. Okay, fine. So how many of you can quickly recall, just because you have completed quiz one? I guess almost everyone can recall. What are the two conditions required for verifying that a given function is a linear transformation?
Addition
Scaling.
and scaling.
Yeah, sorry. What was it?
Addition and scaling.
Addition and scaling. Okay. So what you mean by addition and scaling is that suppose you have a transformation tree from R2 to R2 and you have two vectors, let us say U and V in R2, then you have T of U plus V is equal to T of
T
U.
of U plus T of V separately.
So this is the first condition, and the second condition is that T of alpha U is equal to alpha.
Alpha T of U.
Yeah. So this is for alpha in R. Okay. Good. Now, let us say you have a linear transformation from R2 to R2 with respect to the canonical basis. This is the matrix representation, let us say. Okay. Now, what is range of T and null of T? Range of T is nothing but the set of all TU where U is in R2. So, this is the usual definition of range of any function, right? So, if you have a function, this is how the range of a function is also defined. So, the set of all TU where U is in the domain. Okay, so here this R2 is referring to the domain. Okay, and can you tell me range of T, is it a subset of the domain or codomain? In this case both are R2, but how should we view it? As a subset of domain or codomain? See, U is here and TU is here, right? So now can you tell me range of T is a subspace of,
TU.
yeah, so it is in the domain or codomain?
It is maybe
This
codomain.
is, yeah, so this is domain, this is codomain. Okay, so it is a subset of the codomain. Why it is important is that later on we will be looking at a general scenario where you have m n, not the same spaces. Okay, so from now on we can get used to this concepts here. Okay, now null of T is a set of all U in RT such that AU equal to 0 or equivalently TU equal to 0. Both are going to give you the same answer. Okay, so the set of all U in R2 such that AU equal to 0 or TU equal to 0. Okay, now null of T you should visualize as a subset of which space?
Null of T is in domain.
Null of T is in
Domain.
domain.
U.
Okay, okay, fine. Okay, so null of T is in the domain of this function transformation T. Okay, so you should visualize this as a subspace of the domain. Okay, okay, fine. Now range of T, okay, range of T can also be defined as span of, in terms of A, if you want to define. See, for null the definition is almost the same. Okay, either you can consider it as the solution of the homogeneous system A equal to AU equal to 0 or just TU equal to 0. And range of T in terms of matrix, how can you describe? So in terms of the matrix you can describe it as span of columns of A. Why is that so? Why is that so? So
Trans
T,
AT.
sorry?
A transpose.
Okay. So instead of TU, suppose you had AU, then what will you get? Suppose, so let us say U is equal to U1, U2. Okay. Now, what is AU? Multiply and tell me.
Uh, AU1 plus BU2 and CU1 plus DU2.
Okay, so you can clearly see this is a linear combination of the columns of A. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay, so this is nothing but, so if I'm writing it as AU, what does it mean? It means that the range of T is nothing but span of columns of E. Why? The reason behind that, do you all see this reason here? Okay, all right. Now, dimension of rank of T. What is the dimension of both of these are subspaces? We have already seen that, right? So, dimension of rank of range of T is rank of T, and dimension of null of T is nullity of T, right? And rank of T is the number of linearly independent rows or columns of A. This also we have seen. Why? The reason here is that span of columns is the range. So, the number of linearly independent columns should be the uh, dimension, right? So the linearly independent column will form a basis for the range. Hence, the number of linearly independent columns of A is the rank. And why we can also consider rows? We have already seen that then for any matrix, the number of linearly independent rows are same as the number of linearly independent columns of A. All right. Okay. Now consider this matrix A is equal to minus 2, 3, minus 4, 6, which represents a linear transformation S. What is the dimension of the range space of S? How can
1.
you answer is
1.
1. Why is it 1?
Because we can represent the second vector in the form of first vector.
Please be careful. Here you have one negative sign and one positive sign. And
Rank will be 2. 2. Rank will be 2. It is a full rank matrix.
only if both the signs were same, then what you are saying is correct. Now here it is minus 2 comma 3 and here both are negative. Okay, so you miss that. Other, if the signs were same, then what you are saying is correct. But here the signs are different. So one vector is not a multiple of the other. And so here you see that. So the columns are linearly completed. Columns of A are linearly,
Independent.
come on. Yes, yes, yeah, fine, fine. So this is linearly independent, and hence rank is
2.
2.
yes, very good. Rank of S is 2. Very good. Okay, fine. So we know this is the rank nullity theorem for T. This is only for T from R2 to R2, right? So we have the following. So here, what are the corresponding dimensions? Can you say? So if the range is a plane, what is the dimension?
2.
4.
Okay, if it is line
1.
1.
and origin, it is 0, right?
0.
So similarly, if it is 2 here, here it should be 0, 1, 0, 2, because the sum should be 2 in each case, right? Rank, this is your rank and this is your nullity. All right. Okay. Now consider a linear transformation S from R2 to R2. Which of the following can be the range and null space of S? So here this represents a line, this represents a line. So line and line, is it possible?
Yes, ma'am. It is possible.
Okay. So now the range is entire plane and null is a line.
It is
So
not
here
possible.
this is not possible, right? If it is a plane, then here it should be origin, right? So in this case both are line, so it is possible. What about this third case
It is not
Not
possible.
possible.
and fourth one?
Possible.
It
Possible.
is possible.
Okay, good. Suppose W is a subspace of R2 and T from R2 to R2 is a linear transformation, then dimension of T of W is always less than or equal to dimension of W. It cannot exceed the dimension of W. Okay, so suppose you have, this is your V, let us say. Okay, so that is V is here R2. Okay, and this is the domain and codomain. Okay, and here you have a subspace W. Okay, either it can be W, can be either R2 or a line or just zero, it can be anything. Okay, then what about your T of W? What about your T of W? This has always dimension less than or equal to the dimension of W. So this means what? If your W has dimension 2, so if your W is R2, so if W is R2, then what are the possible options for T of W? It can be any
1
of
and
this.
2.
So it can be any of this.
2
0 also.
1.
Yeah, any of this is possible, right? But if your W is line, then what are the possible options for T of W?
1
0
0.
1.
Either it should be again line or it should be origin. Okay, and if W is just origin, then T of W should be
Origin.
origin. Okay, so that is what this note says. We have already seen this also. Okay, now consider the matrix M of T, which represents a linear transformation T. Determine the output space. What is mean by output subspace? Range, right? Range of T.
Yes,
Yes,
ma'am.
ma'am.
Range.
Outputs of T means range of T. When the input is the line, x plus 2y equal to 0. So your W here is nothing but set of all x comma y in R2 such that x plus 2y equal to 0. So they are asking what is T of W. How will you identify what is T of W? So for that, what you can do is that you can find a basis for W first of all. What is the basis for W? How can you find a basis? You have to rewrite this expression, right? So if you rewrite it in terms of y, what will you get?
X is equals to minus 2y.
Y is equal to, let's write it in terms of y. So y is equal to minus x by
X by 2.
2. Okay, or I guess as you told, maybe in terms of x is reduce our computation, maybe I'll write it in terms of x, so minus 2y. So I'll replace x with minus 2y, and here you have y such that y is in R. So the same set can be rewritten in this way now. Now from here we can easily find a basis. I can take the y commonly. So minus 2 comma 1 y in R. So you see that minus 2 comma 1 is a basis of W. Okay. Now what is T of minus 2 comma 1? Remember now W is a line, right? So what are the possibilities for T of W? So T of W,
Line or origin?
so it can be line or origin. Okay, fine. Now T of minus 2 comma 1, what is that from this given matrix? 1 minus 1 1 1 minus 2 1. Was it what it is?
First would be minus 2 plus 1, and then 2 plus 1.
So it is
Minus 1, 3.
okay. So which of these lines given here contain this vector minus 1 3?
D.
D.
D, right? So not this. So here minus 1 plus 3 into 3 is actually 8, right? And here minus 2 plus 3 is 1, again non-zero. And here you see 3 into minus 1 plus 3 is 0. And for the last one, 3 into 3 plus 1 is again not 0. Alright, so option C is correct. Is this clear for everyone? Yeah?
Yes, ma'am.
Yes,
Okay,
ma'am.
good. Now let us look at what are composition of linear transformations. So you all already know about composition of functions, right? How do you do composition of functions? Let me see how many of you can recall what is composition of linear transformations, or just functions. So let us say f of x is equal to x squared and g of x is equal to x plus 1. What is f of g of x?
So first we will write f. Inside that whatever we have at g of x, then we will put that x plus 1 is equals to x plus 1 whole square.
Okay, so here instead of g of x, we will first write x plus 1 here. Now in place of x plus x, I have x plus 1. So this is x plus 1 whole square. Correct. Okay. Now what is g of f of x?
Now first we will write the f of x, which is x square. Then
Hmm.
we will put that value in g of x, which will be x square plus 1.
Okay. So in general, this is how we do the composition of functions, right? So, sorry, just a minute. So in general, composition of functions for composition of linear transformations. How do you do the composition of linear transformations? So if you have T or S here, both are linear transformations from R2 to R2, right? And we let us assume that A and B represent the matrix of S and T with respect to the canonical basis. Okay. Now, what is the matrix representation of S composition T? Okay, it is very easy. We don't have to compute something new. From A and B, we can simply multiply A and B. That will represent the matrix of S composition T. Okay, all right. And how are the range and null space of S composition related to the range and null space of S and T? Range of see, this is something just rewriting the sets, so don't be too much confused about this. I'll try to explain, but there are several situations where I feel that the students feel this is too complicated. See, this is just some rearrangement of the set. So try to listen to what I'm saying, and don't worry too much if you find it complicated. Okay, so range of S composition T, according to the definition, what is the range of any transformation? So if you have range of for example, just T, if you have, it is set of all Tu such that U is in R2, right? So exact same thing we are doing here. So S of S composition T of V is S of T of V. So first we are just writing the definition of range. In the second step, I'm again exploring the definition of range. So what is the definition of range? So here set of all TV such that V is in R2 is nothing but the range of T. So I can replace this TV as just V in range of T. Why I am replacing TV as V in range of T? Is that clear? How I can do that? Because it is just the definition. Set of all TV such that V is in R2 is nothing but range of T. Okay?
Okay.
All right. Now null of S composition T is equal to set of all the set of all V in R2 such that S of T of V equal to 0. Now here again, what is the definition of null of S? Set of all, yeah, V such that SV is equal to 0. Set of all V such that SV equal to 0. Now here you see that inside here, maybe instead of V, if I put some W, I can just compare. Set of all W such that SW is equal to 0. So let us think of this as the W. Okay. Now I can say that we are considering the set of all vectors for which SW is equal to 0. So here this TV is nothing but all the elements in the null space of S. Okay, set of all V in R2 where we are considering the TVs which are in the null space of S. So this part also, do you understand why I am able to rewrite this s of tv equal to 0 as tv in null of s? Is that clear?
Yes, ma'am.
Okay, fine.
Yes, ma'am.
Good. All right. If b is
Excuse
yes,
The important thing here is that although S of W is equal to 0, W itself may not be equal to 0. Correct, no?
although s of w equal to 0, w itself need not be 0. Exactly. Yes. Okay. Fine. If B is invertible, then the column space of AB equal to column space of A. Okay. So if you have an invertible matrix B, then the column space of AB is same as the column space of A. So these has some simple proofs. So those who want can try to explore it yourself. And if you have difficulties, we can discuss. These are some simple proofs you can explore it yourself. You have to use the property that B is invertible. If B is invertible, then what happens to the rank or what happens to the determinant? You can use the inverse of the matrix and everything. Okay. So here, if A is invertible, null of AB equal to null of null space of B. Okay. So these things and all, you need to explore the properties of invertibility of a matrix. Try to solve this yourself. This is something to check your understanding of how far you are able to use the concepts when you are trying to do some proofs. Okay, so both these things are very simple proof which involves the properties of invertibility of a matrix. Okay, so you can try this yourself. Okay. All right. Now let us consider scenario where you have two transformations S and T, both of which are having dimensions rank to be 2. So you have rank of S is equal to rank of T is equal to 2. So now in this case, so maybe I'll write an example. So just a minute. I'll take an example. Okay. So let us have A is equal to, or let us say we have to S where determinant of, what should be, if A represents the matrix of S, what should be the determinant of A?
Non-zero.
Non-zero. Similarly, B represents the matrix of T, and then determinant of B should also be
Not zero.
okay. Now, what is the matrix representation of S composition T?
This may be zero.
ST.
It is
Oh,
A.
sorry, AB. AB.
Okay, so the matrix representation is AB. Now, what do you know about determinant of AB? You know that you can split them and write it as determinant of A into determinant of B. So, both are non-zero. So, this is also non-zero. Okay, so if this is non-zero, what can you say about rank of AB?
Full
Whole
rank.
rank.
Okay, so if rank of S and rank of T are 2, then rank of S composition T is also 2. Okay, and in that case, what is the nullity?
0.
Zero.
Zero.
Clear? Okay, so let's look at the next case. So now rank of T is equal to 2. You don't know anything about S. Okay, so in this case, what is the range? What is the range of T in this case?
R2.
R2, right? Now, what is the range of S? By definition, it is the set of all
Mm,
SV V in R2, right? Okay, now what is range of S composition T? Range of S composition T we can write as S of range of T. Is that fine? Range of
Yes.
S composition T is S of range of T. right? So here also maybe I'll write. So this is nothing but S of range of T, right? So the image of the subspace range of T, but range of T is R2, right? So can I rewrite this as S of R2? The range of S is nothing but S of R2, right? So S of R2 here is nothing but range of S. So it is just some simple rearrangement. We can see that when you have range of T is R2, that is rank of T is 2, range of S composition T is same as range of S. Can you see that? Yeah? Yes
Yes.
or no? Okay. Now another thing I told you. So range of S composition T is nothing but span of the columns of
AB.
AB, right? So you see that range is nothing but column space of AB, correct? And here what
Yes.
is this? This is column space of,
Space of A.
right? Column space of AB is same as column space of A under the condition that here B is invertible. So do you see how we got this property here? If B is invertible, column space of AB is same as column space of A. Fine. We have just used some basic definitions here, nothing much. Okay, fine. Now rank of S composition T plus nullity of S composition T is 2 according to rank nullity theorem, right? Now we know that rank of S composition 2 S composition T, we can rewrite it as 2 minus rank of S, nullity is equal to 2 minus rank of S composition T. But what is rank of S composition T? It is same as rank of S. But what is 2 minus rank of S? We can write it as null of S. So here this means that from here what can we say? The null space of AB is same as the null space of,
A.
see, but here there is a catch here. Here, okay, here it is given as B. Okay, here they are talking about nullity. Whenever we are talking, here it is nullity actually, not null of S. So we are talking about the dimensions. Just because the dimensions are same, the underlying spaces need not be equal. Please keep that in mind. Just because the dimensions are same, the underlying spaces need not be same. From here, so we cannot conclude this fact. But here you already have the range is equal to range, and from that we gain this obtain this inequality about rank. So here we are able to say the first statement from this part, but here we are talking only about the nullity. So dimensions cannot give the inference that the underlying spaces are equal. So this we cannot prove it from here. Okay, but yeah, we can do it very easily. Maybe I have done it here, let me check. So now column space of AB, this is the definition. Null space of AB, this is the definition. So if B is invertible, column space of AB is equal to the column space of here. So the proof, we saw it from here. So the proof is here for this part. Okay, now if A is invertible, okay, if A is invertible, what do you know about the solutions of Ax is equal to 0 if A is invertible?
Only 0, 0.
Yeah, only 0. So x should be 0. Now if I'm considering, now I want to prove that, so I want to show that null of AB is same as null of, when A is invertible, null of AB is same as null of B. So this is what I want to prove. Okay. Now if I'm taking any vector x in null of B. So what is ABX? Already BX is 0, right? Because x belongs to null of B, BX is 0. So ABX is A of 0, so 0. So this implies that X belongs to null of AB. So one side equality we have already obtained, that is null of, so from here we get that null of B is already a subset of null of AB. Up to this, is it fine? One side equality we have proved, is that fine? Yeah. Now to prove the other side inequality, we have to consider, let us say X is an null of AB. So the other side, now I am taking X from null of AB. Right? So now ABX is equal to 0. Now according to the invertibility property, if ABX is equal to 0, then BX is equal to 0. Right? Because A is invertible. Now Bx is equal to 0 means X belongs to null of B. So this means that null of AB is a subset of null of B. So null of B subset of null of AB, null of AB subset of null of B implies null of AB is same as null of B. Is that clear now? Yeah? This proof, is it clear for everyone? Okay? Good.
Excuse me.
Yes.
Uh, this is all working because of the idea that the matrix and vector multiplication, it proceeds in some sense from right to left. So we take a vector x on the rightmost side, and then when we do bx, we are generating a new vector, and then we are operating a on this newly generated vector. So all we can do is take the matrix on the left hand side and use it to transform whatever vector we have on the right hand side. This is why we are sort of dependent on which vector we generate out of our first multiplication, and then use the second multiplication to see how that vector now changes based on the second transformation. This right to left thing is crucial to this whole idea. Is that right?
Yeah, see, yeah, the matrix and vector multiplication, that is how we are defining, and hence that is playing a role here. Okay. So also when you have this left multiplication, but that is not very commonly considered. For example, in left null space, you do the vector and matrix multiplication from left. Otherwise, it's usually the matrix and vector multiplication is done in this way, and hence the concept goes in this order. Yes, correct. All right. So now, okay, when is the multiplication of two numbers? Let us say you have two numbers. Okay, let us say you have two numbers, alpha and beta are real numbers. Now, what does it mean by alpha into beta equal to 0?
One is 0.
Alpha is 0 or beta is 0 or both are 0. Right? This is the only possible scenario. Yes. Now, suppose A and B are matrices. Now, A into B is 0. What does this tell you? Can we say A equal to 0 or B equal to 0? Do we have this?
This both the matrix may be non-zero, but their product may be 0.
Okay. Yes. So this concept that the product, if it is 0, either one of them is 0, is not required for matrices. Right? Okay. So then when will the composition be 0? Okay. So the first obvious case is when both of them are 0, we will have the composition is also 0. Okay. Or if rank of S is equal to 2, then what happens if rank of S is equal to 2? Then S composition T can be 0 only if T equal to 0. Because what happens if S composition T is 0? This means that AB is 0. Right? So this means that determinant of AB is 0. So this means that determinant of A is 0 or determinant of B is 0. Right? So this we have. Now here, what is that we are having? Rank of S is equal to 2. So rank of S is equal to 2 means what? What is the determinant of A?
Determinant of A is not 0.
Non-zero. Now determinant of, So this implies determinant of B is
T is 0.
0. Okay. Now from determinant of B is 0, how can we say that T should be 0 for S composition T equal to 0?
I don't think we can
Because it's
directly say
depend.
that.
Yeah, think and tell me. What are the possible scenarios? So here, what is the range?
Uh, Range of T.
So here, yes. So range of not S composition T, rank of S is equal to 2. So what is range of S range of S? Range of S
R2.
is R2.
R2.
Now S of T of X is your null space. Now you know that this is 0 for all X. Now what can you say about the Tx? Now if this is 0 for all X, the Tx should be
0.
0 for all X, right? So here T should be 0 in that case, otherwise we cannot say that T is equal to 0. So yeah, here S of T of X is equal to 0 for all X. So in that case, Tx has to be 0. Okay, so think
Ma'am,
of this proof in a more deeper way. Think about how this will work. Okay, so I have given an outline and hint of how this is possible. Think about this in a more detailed way. I have tried to given all the hints required for understanding this. Okay, in a similar way, you can observe this as well. If rank of T equal to 2, then S composition T equal to 0 if and only if S is equal to 0. Okay, so try to understand this from the basic definitions and properties. Okay,
Excuse me.
yes,
If T of X is 0 for all X in R2, then that means the entire R2 is in the null space of T.
exactly. So it means that your T is actually the zero transformation. So it takes every vector to 0. We call it T equal to 0. The notation is T equal to 0. Okay,
And that can only happen if
yeah, if T of X is equal to
every A, B,
0,
C, D inside T
yeah,
is
for
0.
all X, we write it as T is equal to 0. Yeah, if all A, B, C, D inside the matrix are 0, only in that case this will happen. Yes. Okay, so this is what is mean by T equal to 0. It means Tx equal to 0 for all X. Okay, fine. So try to think about this more. Okay. Now let us look at the scenario when rank is 1 for both the transformation S and T. Okay, now for example, let us consider the scenario when you have this is your A, this is your B. Okay, clearly rank of A, you see only one non-zero row, so rank of A is 1.
1.
Similarly here the second column is a multiple of the first column, so rank of B is also
1.
1. Okay, now what is the product? The product is 5, 10, 0, 0. You can verify that and you can see that rank of AB is also 1. Okay, here in this case S composition T is non-zero. Okay, now in the second case, so this is your A, again the same A we have considered where rank of A is equal to 1. And here this is your B where rank of B, what can you observe again? You see that the rows or the columns, they are multiples of each other. So again, the rank is 1. Now what is S composition T? The matrix is A into B, which is the 0 matrix. In this case, S composition T is 0, but S is non-zero and T is non-zero. Okay, so both these scenarios are possible when you have rank 1 matrices. Okay, so here you see that AB is 0, but what about BA? BA is non-zero. Okay, So product of two non-zero matrices can be all zeros. Okay. So you see, so much of strange things can happen with matrices. Okay. So either you can have the product to be non-zero, or the product can be zero. Even if you take the product the other way around, you see that BA can be non-zero. Okay. Fine. Now, let us take a specific example. First of all, I'll suggest everyone take your paper and pen. Try to compute what is decomposition S of x comma y. First compute this and tell me. And then we will calculate the range and null.
um, T of S will, I mean, T composition S is coming out to be row 1, 1 comma minus 3. Row 2 is minus 1 comma 3.
Okay, you have directly computed the matrix. I wanted the transformation actually. So the
X
transformation,
minus x minus 3y, 3y minus x.
yes. Okay, so in this case, the matrix of decomposition S is 1 minus 1 and minus 3. Okay, is that fine?
Yes, ma'am.
Okay, now tell me what is range of decomposition S and null of decomposition S. Maybe you can give me a spanning
One,
vector.
one.
So it is the span of which vector?
1 minus 1.
Yes. And null. So first let me write the set and then we can write it as a span of some vector. So it is x minus 3y equal to 0. Correct? So which is a span of which vector? So if I am replacing x with 3y, it is 3y comma y. So y times of 3 comma 1. So span of 3 comma 1. Fine? Yeah?
Yes, ma'am.
Excuse me,
Yes,
Yes.
ma'am.
I am not comfortable with that because if I do the row reduction operation, I will end up with 0 in the second row. Correct, no?
Yes. Correct.
So on the basis of that, okay, fine, fine. No, no, I'm okay with it because we are taking the vector of the original matrix, so that's okay. That's okay.
Okay.
Thank you.
Okay. Okay. So here it is x minus 3y. Okay, so this is the range and this is the null. Okay, fine. Now we have another question here. Everyone try to verify this. Consider two matrices A and B representing linear transformations T and S respectively. Which of the following options are true? Try to think and answer. Don't be in a hurry, take time. Sorry, there is some background noise in my place. So
Is zero.
Ma'am, option A is true. Option B is not true.
okay, so option A is true and B is not true. Okay, what about option C and D? Check that as well.
D is true, C is false. As range of T, I am getting a span of 1 minus 1.
Okay, okay. So let us see that here. See, I have computed A, B, and B. So from that, I have given the answer. So was the same technique used by all of you, or did you do it in a different way?
Same method.
Same
Same method.
method, right? So here you see the range of T composition S. So here that is 0. So here A is this and B is this. So T composition S is 0 because of this, right? And S composition T is non-zero, right? And from here you see range of T is span of 1 minus 1, and range of S is span of 2 comma 1, right? So now this is your BA, and here from this you can say range of BA is span of which vector? Again 2 comma 1, right? 24 12 is product of 2 comma 1, right? Yeah, so both are alpha times of 2 comma 1. Here also both are alpha times of 2 comma 1, right? So range of S composition T is same as range of S in this case. Okay, and range of T composition S is already 0, but range of T is non-zero, so this is incorrect. Is that fine for everyone? Yeah.
Yes.
Okay, good. Okay. So in general, what are linear operators? So far we have seen what are linear transformations. Now we are going to move to a more general setting. So we can have linear transformation from R2 to R or R2 to R3, right? So a linear transformation usually refers to any transformation from Rm to Rn. Okay. Now, if the domain and codomain are different, then we usually call it linear transformation. If the domain and codomain are same, so in this case, for example, m is equal to n, then we call it a linear operator. So a linear transformation T from R2 to R2 is a linear operator, right? So now for this following question, can you first of all tell me what is the domain and codomain in each case? And from that, we can say whether it is a linear transformation or linear operator. What is the domain in the first case?
R2.
R2. And codomain?
Also R2. No, it's
Be
linear.
careful.
R.
R. So in all the cases, it's R2 only. Domain is R2. So what is the codomain in this case?
R2.
Okay. What about
R2.
this one? R2. Here?
It's not even linear.
Yeah, but the codomain is R2, but this is not a linear transformation. Okay, maybe I'll write not a linear transformation. Let's not use unnecessary symbols and confuse. Not a linear transformation. Okay, so what about this? This is a linear transformation. This is a linear
Yes, ma'am.
operator and hence also a linear transformation, right? And what about this? Again, the same linear operator and hence also a linear transformation. Okay, fine. A very basic question. Okay, now we are going to.
Excuse me.
Yes.
If in B we had x plus y comma anything but 0, we would lose that one also, correct? No?
Not necessarily. Here, if
If
we
we
have,
had x plus y comma 1, then we have lost the
oh,
linearity, I
you are
think.
you are saying it, but any constant. In that
Huh.
case, yes. Yeah, yeah, yeah.
Also, the D part, are we saying it is non-linear only because of the xy, or there is some other reason as well?
That's the only reason. So this cannot happen for a linear transformation.
Which property have we lost exactly? For example, in B, we can see that anything other than 0 over there would make us lose the additive identity. Very clearly, we will not be able to add anything and leave the vector unchanged. Here, what is the loss? Is it the multiplicative identity or something else?
So let us maybe check about t of 1 0. What is t of 1 0?
0
0,
comma 1.
1.
0 comma 1. What is t of 0 1? 0 comma minus
Minus 1.
1. Okay. What is t of 1 comma 1?
1 comma 0.
1 comma 0. But you can see that clearly t of 1 comma 0 plus t of 0 comma 1, it is not same as t of 1 comma 1. Correct? It should have been equal, right? For a linear transformation. Got it?
Yes,
Okay,
ma'am.
thank you.
Yeah.
Thank you.
All right. Okay. Now we are going to look at matrix powers. Okay. Fine. So why we need linear operators for matrix powers? Because if we are going to look at powers of a matrix, the matrix should be a square matrix, and square matrix comes only for linear operators. For general linear transformation, the matrix can be rectangular, and so we cannot talk about powers. And hence, while we are talking about matrix powers, we are looking only at linear operators. Okay. So now we know that if you have t from r2 to r2, and a is a matrix with respect to r with respect to t, right? Then for t power n, the corresponding matrix is a power n, because what is t power n? So for example, t squared is simply t composition t, and t power n is t composition n times composition of t, right? And you know that the matrix of t squared is a square. So the matrix of t power n should be a power n, right? So for t power n, the corresponding matrix is a power n. Okay. So now with this, can you figure out the answer for this?
A.
A is correct.
Okay. So 1 0, you will get 0 4, and then you have 3 0. Yes, A is correct. And then
Sorry, what is this m of t squared really?
m of t square is the square of this matrix, m of t. Maybe if I have a bracket here. So if I call this A, what is A square?
B is not correct.
Okay, so what should be the square of the matrix?
12 0 0 12.
It should be D option.
Yeah. Okay, fine. Shall we move on? Okay, fine.
Excuse me.
Yes.
Why are we not just squaring the individual elements?
This is not a diagonal matrix. For diagonal matrix, see, you have to look at the principal diagonal always. So I never call this as a diagonal. See, this will cause a lot of confusion, because people tend to take the properties which are there for principal diagonal for this. So this we never consider it as diagonal. only for when you have the principal diagonal, that is when you have aij non-zero for all I not equal to j, that is called a diagonal matrix. So aij equal to 0 for all I not equal to 0. So this is a diagonal matrix. And for diagonal matrix, so for if you want to do a square, then it is aij square. Okay, but in this case it is not the case scenario. Here this is not a diagonal matrix, you cannot do that. Okay, fine.
Also, if we look at this, then is
Yeah.
every matrix which is not having the principal diagonal,
Hmm.
when we square it, we then get a diagonal. Is that true?
I don't think so. You can try it. So what you are saying is that suppose you are having a matrix like this. So okay, so in that case, so we have to look at the structure here. So here the structure, is it getting reversed? That is what we are seeing, right? What we are doing is that t square of x comma y is t of x comma y, right? So t of x comma y. So T of, let us say you have alpha y and beta x. I guess, yes, that's true because of this property. So you have T of, yeah, only one T. Already I have put one T. So here then what will happen? This will get again reversed, right? So what will happen here? So your y will go here. So you will have alpha, beta, y, and this x will come here. So you will have beta x, alpha, beta times of x. So yes, you will get a diagonal matrix. In fact, a scalar matrix, not just diagonal, but in fact a scalar matrix. Okay.
Sorry, what is meant by a scalar matrix?
All the diagonal entries are same. A diagonal matrix where all diagonals are same. Okay.
Okay, so like 12, 12 we have, so
Yeah.
like that.
So it is a multiple of the identity matrix. Okay.
So at that point, we'll be able to just pull the 12 out of the matrix,
Yeah.
and then that 12 alone will be the multiplication factor for
Mm-hmm.
all the even powers of A in this case. Is that correct?
Yes. Yes.
As long as the power of A is even, we can forget about the matrix and just multiply the elements with the scalar that we obtained during A square, and
Yes.
just keep raising that scalar,
Powers.
in this
Yeah.
case 12, to the exponent.
Yes. Yes.
Okay, so any odd power of A will again give us the same form. Is that correct? Of the non-principal diagonal?
Yes, so it will be of this form. So alpha y comma beta x. Okay. So it will be in this form.
So
Okay.
odd powers will take the other diagonal, and even powers will reduce to this scalar matrix.
Yeah, but hold on. So here, if I take the cube, it's not going to get swapped. So I don't think odd powers will take this structure. After this, all powers are going to be just this diagonal matrix only. You see, because what happens here? T cube of x comma y. Oh, I'm applying this. Yes, yes. So you see that t cube of x comma y will be reversed. So some alpha dash y comma beta dash x. It will be of this form. Yes. And all odd powers are of this form. Even powers are of this diagonal form. Yes. Correct.
Okay, thank you.
Yeah. All right, and so the next important part here is that we are looking at vector spaces with complex entries. So the set of all x comma y where these entries x and y both are complex numbers. So for example, a vector here can look like this: 1 minus I comma 2 plus I. Okay, so this is a vector you can see in C2. So R2 is obviously a subset of C2. Okay, and all the definitions, every property we have seen about linear operators from R2 to R2 applies for the linear operator from C2 to C2 as well. Okay, fine. And note that here the scalar field is C. Here the scalar field is C. What does this mean? The alpha which you are considering, we usually take from R. Now you are taking it from the complex numbers. So when you do this T of alpha u equal to alpha TU, we say alpha is from, earlier it was R, now it is in C. So the scalars are from complex numbers. So it can also take real values, but in general it can take any complex numbers. Okay, so these are complex vector spaces. Okay, so what are eigenvalues and eigenvectors? So before looking at what are eigenvalues and eigenvectors, so this is a very crucial part of this course, eigenvalues and eigenvectors. Okay, so before this there are few important factors which we are going to recall. What are they? Any three vectors in R2 are linearly dependent, right? And a linear transformation is invertible if rank of t equal to 2 or equivalently null of t equal to 0. And a linear transformation is said to be singular if it is not invertible, that is if null of t is equal to 0. Okay, so here I am saying it the other way around. So here it should be rank of t is equal to null of, here this is incorrect, right?
Rank of T will be 0.
It need not be even 0. Here it just has to be, or maybe non-zero. If null of t is non-zero, that will make sense.
Determinant of T will be 0, right?
Null of t is non-zero will make sense. Okay. All right. If t is singular, then there is a non-zero vector v. So that is what is meant by null of t is non-zero, right? So if t is singular, then we have a non-zero vector such that t v equal to 0. Okay. Fine. So why we need this? Once you see the definitions, you will understand. A complex number lambda is said to be an eigenvalue of t if t minus lambda I is singular. Okay. So this definition, why first of all do we need a complex number to define? Why not just a real number? Okay, we will see the answer shortly. So first of all, what does the definition say? Any complex number which satisfies the condition that t minus lambda I, we are looking at the operator t minus lambda I. Okay, if this operator is singular, we call this lambda as an eigenvalue. We also say that lambda is an eigenvalue of the matrix M of t. And how are we going to find the eigenvalues of this matrix? We are going to compute the determinant of A minus lambda I. Because this t minus lambda I is singular, this means that determinant of A minus lambda equal to 0. So all the solutions of this equation are nothing but the eigenvalues of your matrix A. Okay, so let us do some very simple examples to understand this. So for example, consider this matrix. What is A minus lambda I first of all? A minus lambda I is this matrix 3 minus lambda 1 1 3 minus lambda. Now what is determinant of A minus lambda I? What is the determinant? 3 minus lambda square minus 1. And when you expand this, what will you get? Lambda square minus 6 lambda plus 9 minus 1, which is lambda square minus 6 lambda plus 8. So what are the roots?
Or we could just do 3 minus lambda minus 1 and then 3 minus lambda plus 1 using the a square minus b square.
Yes, definitely. So
Values are 2 and 4.
2 and 4.
4, 4.
Okay. Okay. So in this case, we have got real and distinct roots. Both are real numbers and they are distinct. Distinct in the sense that they are not equal. Right? They are different. Okay. Now let's look at the next scenario. Here you have, this is your matrix. Now what is the determinant of a minus lambda I. So here you have 1 minus lambda, 2 minus 2, 5 minus lambda. Now what is determinant of a minus lambda I? 1 minus lambda into 5 minus lambda plus 4. So can you quickly solve this? Lambda square, and then you have
Lambda square minus 6 lambda plus 9.
yeah, plus 5 plus 4, so 9. So which is lambda minus 3 the whole square. Yeah, can I write it as lambda minus 3 whole square? So in this case, determinant 0 implies what are the roots? Both are 3. Okay, so in this case the roots are real and
And equal.
they are repeating. We call it repeated roots. Okay, so the roots are repeating. Okay, so this is another scenario. So let us look at a third scenario. So the third scenario, let us consider, for example, this matrix 0, minus 1, 1, 0. Can you all compute the eigenvalues and tell me? First of all, tell me what is determinant of a minus lambda I, and then you can tell the eigenvalues.
It will stay the same, right?
This is
Yes,
not a
lambda square
diagonal. Yes, lambda square
plus 1.
plus 1.
Lambda is equals to plus minus 1.
Plus minus?
1.
Are you sure?
No, 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 no. Sorry. Under root minus 1. Then it is, I think, I.
Yeah. So here you have lambda is plus or minus square root of minus 1. So lambda is either I or minus I. So in this case, we have complex roots. And note that always we know that complex roots occur in conjugate pairs. What are conjugate of a complex number, you all remember?
Yes, ma'am.
Right? So if you have x plus iy, what is the conjugate? X minus iy. So always if x plus iy is an eigenvalue, x minus iy will also be an eigenvalue. Okay, because the complex roots occurs in pairs. Okay, so what are the three possible scenarios? So either it can be real and distinct, or it can be real and repeated roots, or it can be complex roots. Okay, so for a 2 by 2 matrix, these are the possible scenarios. Okay, so now come to what are
Excuse me.
eigenvalues? Yes.
We had started this by saying that m of t can belong in the complex domain as well, right? It can be from C2 to C2. Right now, we are only calculating when A is R2 to R2, right?
Yeah, we have not considered the complex matrices yet. We will see it slowly. First, we will look at only the real matrices. Slowly, we will also look at complex matrices. Okay.
So the question was, even a real matrix can have complex roots.
Yes, that's why here I told you that this has a reason. See, a complex number lambda, even if t is a transformation from R2 to R2, even in that scenario, you will have a complex number lambda as an eigenvalue, because for a polynomial, okay, a quadratic equation, we can have complex roots even with real coefficients. Okay, that's why in the definition itself, we are telling that the lambda is a complex number. Okay, is that clear? Okay,
Yeah, okay. One thing I wanted to ask,
yeah.
when we are having this lambda occurring as a complex root,
Mm.
and we say that necessarily it must be in a conjugate pair,
Mm.
then does that mean that if my polynomial has a odd degree, let us say it is a cubic, or we have a power of 5, the degree is 5,
In
then if
that,
complex root can only occur in pairs,
mm,
then the odd number will be taken by the real root. Is that how it works?
So here, whenever you are having a odd degree polynomial, and you know that, see, for this is kind of a theorem also. I forgot what was the name. So this is a fact which says that for any odd degree polynomial, you will always find a real root because the complex roots occurs in pairs. So always any odd degree polynomial will have a real root because of this reason. Got it?
So there will be that one real or three real or five real, whatever it is,
Exactly.
but the remaining missing root will be taken by a real number because the complex one will always occur in pairs.
Yes.
Okay, thank you.
Okay. Okay. So I guess now you all understand what is meant by an eigenvalue and how to compute it. I guess now that part is clear for everyone. So we can move to the next part, which is eigenvectors. So what are eigenvectors and how to compute them? Okay. So you all already know how to compute null space, how to compute a basis of null space. So computing eigenvectors are something which you already know, because here is the definition. Suppose lambda is an eigenvalue of an operator t. What do we know? Null t minus lambda. So if lambda is an eigenvalue, it means we know that t minus lambda I is singular. If this is singular, what do we know about null of t minus lambda I? So if this is singular, then we know that this is non-zero. Null of t minus lambda I is non-zero, right? And all the non-zero elements here, okay, that we so all the vectors here together, we are calling it as the eigenspace, and the non-zero vectors are called the eigenvectors. Okay, so remember, always an eigenvector, see, I'm putting it in red, an eigenvector should be non-zero. Remember this very clearly. An eigenvector should be non-zero. This is how we are defining an eigenvector. Okay, so eigenvector should be non-zero. Now for every eigenvalue, there is at least one non-zero eigenvector. Okay, why? Because this null space is non-zero, so we can obviously find at least one non-zero eigenvector, right? Because this is non-zero, this means what? The dimension is at least one. Okay, so in other words, there is a non-zero vector v. So this is the usual definition which we are considering. So tv equal to lambda v, where v is non-zero. So if you have such an equation, then we say that lambda is an eigenvalue with eigenvector v. Okay, so this is the usual definition you can see in many places for eigenvalue and eigenvector. Okay, so now based on the things which we have seen, first read this options given here, and then we'll discuss which one is correct or not.
Excuse me.
Yes.
For clarity, when we say t minus lambda I, we
Hmm.
are making that square matrix. We are essentially building up that t minus lambda I thing, and
Hmm.
then we are multiplying that thing with some vector xy,
Hmm.
right? And that is how we are generating this eigenvector. Is that correct?
See, yeah, you can see that these are the vectors in the null space. So, which means that we are looking at t minus lambda I times of v is equal to 0 vectors, which satisfies this. So, when you are rewriting this, it is becoming this. So, which is same as tv equal to lambda v. So, this any vector in the null is same as saying any non-zero vector which satisfies tv equal to lambda v. Yes, Manish Shankar, what's your question?
Madam, I can't understand this eigenvector concept clearly.
Okay. See, what are eigenvectors we want to see. So for that, first, what are eigenvalues? That definition, I guess you understand, right? So the definition is that, so you take t minus lambda I. Okay. So when, if lambda, all lambda such that t minus lambda I singular, they are called the eigenvalues of t. They are called the eigenvalues of t. Now, T minus lambda I is singular. This means what? My null space of T minus lambda I is non-zero. So this means that, so null of V, so there are some non-zero vectors here. Okay, so now my this is called the eigenspace. What is an eigenspace of T? So eigenspace of T is simply the null of T minus lambda I. Okay, and this is non-zero. Okay, now the non-zero vectors in null of T minus lambda I, they are nothing but eigenvectors of T corresponding to this specific lambda. Okay, when we do problems, you will understand it even better. Okay, so what are eigenvalues? All lambda such that T minus lambda is singular. So for that, because singularity, we have determinant of A minus lambda equal to 0. This is what we are using. Now, because it is singular, the null space is non-zero, and this null space is the eigenspace. And all non-zero vectors in this null space, they are called the eigenvectors of T corresponding to lambda. Right? So suppose let us say V belongs to null of T minus lambda I, where V is non-zero. Then what will you have? T minus lambda I times of V equal to 0. So this means that TV minus lambda V equal to 0. So this means that TV equal to lambda V. Okay, so we can also say that eigenvectors of T corresponding to lambda are nothing but non-zero vectors satisfying this equation. Okay, all are equivalent definitions. Okay, so now do you understand the definition clearly, Manish Shankar?
Yes, ma'am.
Okay, fine. So now looking at this problem here, consider a linear operator T from R2 to R2. Which of the following options are true? For every eigenvalue of T, there exists at least one non-zero eigenvector. Is that true?
Yes, ma'am.
Yes, that's the definition, right? There is at least one non-zero eigenvector. Okay, if V is in R2 minus 0, such that TV equal to lambda V for some lambda in R, then V is an eigenvector. Again, this is the definition.
True.
If 0 is an eigenvalue of T, then the corresponding eigenvector will be only 0, 0. Is that true? First of all, you don't even have to know about what are the eigenvectors corresponding to 0, but can 0 be an eigenvector?
We said it should be non-zero, correct?
Yes. The eigenvector can never be 0, right? So it does not matter whether your eigenvalue is 0 or not. Your eigenvector can never be 0. I will show you some examples of how the eigenvectors of 0 corresponding to the eigenvalues 0 will look like. So forget this. Eigenvalues of a diagonal matrix are the diagonal elements. Why? Because determinant of A minus lambda I will be simply what? Lambda minus A11, lambda minus A22. So the roots are nothing but the diagonals. Right? Same way you can see that in the determinant of A minus lambda in both the scenario is this. That's why the eigenvalues are just the diagonal elements. You can check this for any diagonal matrix. Okay, fine. So
Excuse me,
yes.
one question came to mind. When we are writing that polynomial equation for finding lambda itself, we cannot use that directly to form the eigenvectors in any way, correct? No? That's something else entirely.
Yes. So just this process cannot help you in finding eigenvectors. You need to do some computations separately, like finding the null space. Yeah. All right. Okay. So here is a problem. First, what is that you observe about this matrix?
lower triangular matrix.
Yes. What did we just see about lower triangular matrix? What are the eigenvalues?
Diagonal elements.
Yes. So you know that the eigenvalue should be 2 and 3 minus 3. So these are the eigenvalues of A. So we know that this is a lower triangular matrix and hence the diagonal elements are the eigenvalues. So eigenvalues computation is straightforward. Now how do we compute the eigenvector? Okay. So for computing eigenvector, we will consider A minus lambda 1i. So for A minus lambda 1i, what is the matrix? 0, 0, 1, minus 5. Is that correct? Is that correct? Your lambda 1 is equal to 2. What is A minus lambda 1 times of identity? Why there is no response? Is this
Yes,
something?
No,
ma'am.
just
This is
looking
true.
at it that we take only one of those eigenvalues at a time, one at a time we will
Yes,
prove
yes.
it.
Okay. Now we are going to look at what is the null space of this. So we are going to look at what are the vectors which satisfy this condition. So you have 0, 0, 1 minus 5 xy equal to 0, 0, which means x minus 5y equal to 0. Okay, so you see that what is the eigenspace? Your eigenspace for lambda 1 is set of all x comma y such that x minus 5y equal to 0. So can you tell a basis in this case? So this is a span of, instead of
5
x,
5
comma
comma
1.
1.
5 comma 1. So in this case, note that if v is an eigenvector of A with respect to lambda, then alpha v is also an eigenvector. Okay, so if v is an eigenvector, then alpha v is an eigenvector. So if 5 comma 1 is an eigenvector, can I say minus 5 comma minus 1 is also an eigenvector? Yes. Okay, so you take any non-zero vector in this eigenspace, that will be an eigenvector, not necessarily 5 comma 1. Suppose someone is going to write this in this way, so I can write this as span of, instead of x is equal to 5y, I want to write y is equal to minus 1 by 5 times of x. Then what will I have? I will have here, so 1 comma 1 by 5. So in this case, can I say that, so this is a eigenvector. This is also an eigenvector. They are just multiples of each other. So any non-zero vector in this space is an eigenvector. Okay, so is this concept clear for everyone? If V is an eigenvector, then any alpha V is also an eigenvector provided this alpha is non-zero. Is that clear? Yeah.
Yes,
Also,
ma'am.
it seems that V will always be closely associated with its particular eigenvalue.
Yes, yes. Because, yeah, you see that it is a null space of A minus lambda 1i. We are talking with respect to one specific lambda. This V is always associated to some specific eigenvalue. It is not just about the matrix, it is also with respect to some specific eigenvalue. Okay, if you are changing the eigenvalue, then the eigenvector will also change. Okay, so for example, here itself, if we are looking at A minus lambda 2i, then what will be the eigenvector? A minus lambda, what will be an eigenvector? So here, what's the matrix you will get? If I am subtracting minus 3i, so here you will have 5, 0, 1 and 0. Correct? So xy equal to 0. So this means your x is equal to 0. So what should be an eigenvector? X is equal to 0 means 0, 1 can be an eigenvector, right? So you see that in this case, span of 0, 1 is your eigenspace, and any non-zero vector from here is an eigenvector. So which options are correct?
Option D.
Option D and option A. Fine. Okay. So finding eigenvectors, is it clear for everyone? Yes or no?
And
Yes,
again,
ma'am.
every time we say,
It will be more clear during the assignments. We will try more.
Yes, yes, yes. Okay. So just for you to understand how does the eigenvalue corresponding to 0 look like, I want you to do some specific example. So just try this. I will give you a very, very straightforward question. Try this one. So find the eigenvalues and eigenvectors of A is equal to 2, 1, 0, 0. Very easy matrix. What are the eigenvalues? Is it possible to say it straight away?
diagonal elements you said, no, for any upper
Yes.
triangular.
Yes.
So 2 and 0 themselves.
Yes. Okay. So specifically the lambda 1 equal to 2 part I will let you to compute by yourself. I want you to specifically compute the eigenvectors corresponding to 0 now. Maybe this part you can do later. Can you do this part for lambda 2? So eigenvector corresponding to lambda 2 equal to 0. For
That
that,
is just the null space of A itself, right?
exactly. Exactly. So this is nothing but the null space of A, right? So this is a very important observation. This is nothing but the null space of A. Okay, so
Because lambda I is just a bunch of zeros,
yeah,
complete zero.
yeah.
So if we subtract that to A doesn't change at all in any way.
So here AV equal to 0 will give you 2100 xy equal to 0, 0. So you have 2x plus y equal to 0. So here maybe you can write span of maybe 1 comma minus 2. Okay. So you can see that 1 comma minus 2 is an eigenvector for lambda 2 equal to 0. Yes. Anyone is having questions here? Okay, so how does an eigenvector of lambda equal to 0 will look like? They are nothing but the non-zero vectors in the null space of the matrix. Is that clear to everyone? Yeah. So the other part, eigenvector for lambda 1 equal to 2, I will leave it as a homework. You can try. It's quite straightforward. Okay. Is it fine? Clear for everyone?
So we said that it's all the non-zero vectors of the null
Yes.
space.
Yes.
So now going back to that equation you had written, TV is equal to lambda V.
Mm.
So any transformation can be represented as lambda V. We know that lambda in this case is a 0 and the vector associated with is a null space vector minus 0. So now what do we have here? TV is going to end up in the 0 anyway, and the lambda V will also end up in 0. So we have a 0 equal to 0 equation for this particular situation. Am I seeing it correctly?
No. See, first of all, any transformation cannot be written as lambda v. Okay, so it depends on what is your lambda we are talking, right? So what is your v and what is your lambda matters. So here, for only some specific v, we can write tv as lambda v. So you cannot write the whole transformation T itself as lambda times of something. That is possible only if you have a scalar transformation, right? Okay, so only for some specific non-zero vectors, okay, the left hand side, okay, so TV, one, you are taking a vector from the null space, okay, and here you are having lambda v, which is here lambda is 0, so this v is in the null of T, and here this is 0. Okay, so this is basically the definition of null space of T. Okay, so viewing it as both left hand side and right hand side 0 does not sound very nice. So it cannot be wrong as well, because TV I am saying it as 0. But what is LHS? You should understand. LHS here is TV where V is a non-zero vector. Okay, and RHS, you can see it is obviously 0, because here the vector is the lambda is 0. So lambda V is actually just the 0 vector. Okay, but when you compute TV, you will get 0. Is that clear?
So V, as in apart from the origin itself, we know that null space always has origin. We are throwing out the origin, first
Yes.
thing to do, and
Yes.
then whatever remains in the null space, that we are transforming with T, and that will end up in 0 because it is the null space. So
Yes.
that's how we are getting LHS equal to 0.
Yeah.
And the right hand side is forced to be always 0 because of that lambda equal to 0.
Yes. Yes. Okay.
Okay.
Good. Okay, so moving ahead, we'll look at some important properties of eigenvalues and eigenvectors. So eigenvector, okay, so maybe I don't want to do too much in one session. So understanding eigenvalues and eigenvectors is something very crucial. I don't want to dump too many things in one session. So maybe the properties about eigenvalues and eigenvectors, it's better we continue it in the next session. Okay, we will stop with this part here. I recommend all of you before tomorrow's session, do some examples, go to, look at the activity questions, do some examples and try out before tomorrow's session. Okay?
Excuse ma'am.
Yes.
Yes, ma'am.
Ma'am, till this point, can we get this PDF for?
Yes, yes, I will share. I will share right after the session.
Okay, thank you.
Yes, ma'am.
Okay.
So
All
tomorrow's
right.
session
Ma'am,
is newly created, is it? I didn't see
Tomorrow's
any.
session?
Tomorrow's session, I just checked the calendar. It's there between 10 to 12, same time,
Yes.
right?
Yes, 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 same time.
It wasn't there earlier, so I was just asking.
madam, from this week 5, I think this is very strange. I am feeling it is. We are going towards a strange direction.
It's not a strange direction, it's a new direction. Okay, it's just the topics which you have not seen earlier, so just everything is completely new for you. And when you are going to move to like more higher courses, like advanced courses, you will see the power of eigenvalues and eigenvectors. Okay, so they are called the spectral values in many places, and you know the word spectrum. So many, even like shops and places, websites, you can see like spectrum they keep, because spectrum is something giving the essence of the whole system, right? And the eigenvalues or the spectral values giving the essence of a system. Okay, you will understand why they are the essence when you look at advanced courses and applications. You will understand it better. These are very core of linear algebra, eigenvalues and eigenvectors. Okay, fine.
One question, please.
Yes.
Do we have time for the question, first thing?
Yes, yes.
So when we wrote TV is equal to lambda V, then let us say we have two eigenvalues for this particular situation, for this particular matrix, let us say. So then there will be two associated eigenvectors with each of those eigenvalues. So we'll have lambda 1, V1, and we'll have lambda 2 and V2. So what we are essentially saying is, when we pick up vectors along the line of V1 or V2, and we transform them using T, obviously non-zero vectors. So when we transform either V1 or V2 using T, we will get a resulting vector which we can represent as a scaling of that vector directly. Is
Yes.
that what we are trying to say?
Yes, yes.
So the vector will not change direction if it is lying along v1 or v2. It will not change direction. It will only get scaled by the transformation called t.
Yes.
That is the effect of the eigenvalue, is it?
Yes, but when you look more into the geometrical view, so maybe specifically if we are looking at the geometric point, so how should I? Maybe when we are looking at the inner product spaces, when in which week are we starting inner product spaces? Any idea? I guess in week 8, maybe. Let me just quickly check. So there I can help you to look at the geometric view of this eigenvalue concept. It's in week 9. Okay, so inner product in R2 and C2, we are starting in week 9. So once we understand what are inner products, there you can understand the geometrical point of this eigenvalues. So what is happening? So the vector v is simply getting extended along the same line. It is not moving anywhere else. Also, where is this vector v with respect to t? See, v belongs to null of a minus lambda I. But when you are looking at v with respect to only a, where does this v belong to?
In the domain of t.
In the range of t. It is in the range. Okay, because it is AV, it is of the form TV. What is your range? Set of all TV, right? So your V is actually there in your range.
So it's there in the domain as well as the range.
Yes, this is something special about this specific vectors. Okay.
Madam, in the next session, some images will be more beneficial for us to visualize.
Okay, okay. So tomorrow's session, I will maybe add some Desmos graphs to look at the range and the eigenvalues, eigenvectors to understand it, and maybe a little bit of geometry. Let's not go too much. I will, but try to add some figures in tomorrow's session. Okay.
Yes, ma'am, that will be very beneficial.
Yes, yes. We'll do that tomorrow. Oh,
Also, sorry to bring this up, but I just noticed on your PDF below it says page 8 out of 34. So, are we sure that tomorrow will be enough to go through all
yeah,
of this?
no, no, I don't think all the 34 we have contents. I have just contents maybe till 20 or something, not beyond that.
So, we'll be able to do it tomorrow, right?
Yes, yes, I don't think I have content for the entire 34 pages. I should not have. Maybe, oh, okay, okay. See, these are from dot product. See, this is like contents combined with some other weeks. So all this content of this PDF are not just for this week. So don't worry. So it stops somewhere much before page 20. So inner products and everything is there in this one, which is not in this week 4. So don't worry. So it stops here. It stops here with page number 13 itself. So don't worry.
Okay,
Okay.
no, I was only worried because whether we'll have time to ask questions or not.
Yeah,
Okay.
yeah, yeah. With page 13, we are done. Okay, so see you all in tomorrow's session then. Okay, bye.
Thank you.
Thank you, ma'am.
Thank you, ma'am.